So, if you watch cartoons of any type, you'll often see magnets depicted in this fashion. A horseshoe magnet with a north and south pole capable of pulling enormous amounts of metal from any distance. The truth is not quite so florid. In terms of magnetism, we've known about magnetism for a very, very long time. The Greeks first found things like magnetite attracting iron and wrote this down. People were probably exploiting this before that, but the Greeks wrote a lot of things down for us. Lodestones were used by Vikings in navigation. When it was too cloudy to actually see where they were going, they could find magnetized materials which would actually point in the magnetic north direction and allow them to navigate. Magnetic ferrous material, of course, has been around for a long time in terms of its usage, and here we have just a piece of rock with staples stuck to it. When we talk about magnetism, we refer to a north and a south pole. Those poles are essentially just the two ends of a single bar magnet. And remember, like we dealt with for negative and positive charges, like magnetic poles will repel, and unlike magnetic poles will attract. Meaning if you take the north and south end of two magnets and put them together, you will result in an attractive force between them. Put two north poles together or two south poles together, and you will result in a repulsive force. And here's a typical kind of experiment you could do. And you can take a bar magnet, put a sheet of paper on it, and then sprinkle iron filings onto that magnet. The iron filings will then take the shape of the magnetic field emanating from the magnet. You can do this if you have one of those old toys where you have iron filings and a cartoon face, and you can draw little beards and moustaches on them. Not the most scientific, but it's a fun thing to do. So here's the effective diagram showing the physics of this particular case. If we take two bar magnets, by bar magnets we mean a single piece of material with a north and south pole, magnetic pole I should say. We put them together, the north and south pole will attract, they will feel a force of attraction between them. So a positive force here, negative force here, the two will come together. We take the two north poles and put them together, and we'll end up with a repulsive force occurring. Likewise, if we put the south poles together, we would have the same effect. Now, one of the things about magnetic poles is you cannot have a magnetic monopole, meaning you cannot just have a north end and a south end. So a magnet will always have a north and a south component to it. That means if you take a bar magnet and you smash it in two, you will end up with two new magnets. Smash it into four and you'll end up with four new magnets. You'll always have a north and a south pole to each component of these magnets. So magnetic poles always come in pairs. The magnetic field itself, well, this is really set up through a material here. So here's our magnetic field, and it will spiral around, giving us a nice straight line inside the material. More on how we can exploit this later, and a curved magnetic field on the outside, linking the north and the south magnetic poles. If we want to look at this particular magnetic field, we can take magnets and we can place them in the magnetic field. And rather than pointing towards Earth's magnetic north, those compasses will actually move and point in the direction of the magnetic field itself. So here, the magnetic field is going this way, the compass will align to this magnetic field. Here, the magnetic field is going this way. You'll see the compass pointing west. And that's why you can't really have magnetic materials surrounding any form of compass. If you do, you will end up with a situation where your magnetic navigation will not work so well. And this is the sort of thing you'll see if you sprinkle the iron filings on it. It'll take the shape of this magnetic field. So if you move a magnet near a second magnet, they'll both experience a magnetic field, and those lines are what we were just referring to. The compass needle will point in the direction of the appropriate magnetic field. You can, of course, bend your magnet. You don't have to have one end of each of the bar north and one end of the south. You do still have the bar, but you can bend it so the north and south poles are right next to one another, and that'll essentially reshape your field. Magnetic field lines cannot cross. They can interact, but they will not cross one another. We're not going to get too deeply into what causes magnetic fields. It is involving the alignment of the angular momentum components of the individual atoms. That is really how we're creating permanent magnets. But moving electrons essentially actually produce magnetic fields. And we're going to see this when we start talking about current and the production of magnetic fields from a current. In most magnetic fields, in most materials, I apologize, your magnetic fields will cancel out. Very much as when we looked at electricity. If we touch most objects, we don't get an electric shock. The electric fields all cancel out and you end up with a neutral surface. Very similar with most materials. The magnetic fields will all cancel out and most objects are magnetically neutral. Some materials like iron, cobalt, nickel, etc., they behave as small magnets themselves, and you can align the particles much more easily and end up with a magnet much more easily. These objects will magnetize more than others. Earth's magnetic field is thought to originate with moving charges. There's probably a molten core of iron and nickel deep within the Earth that's flowing, and that's creating electrical currents which are resulting in a magnetic field for our entire planet. There's the magnetic field of our planet. Here's the Earth, very much acting as a bar magnet with a south magnetic pole and a north magnetic pole. Something to be advised is the north magnetic pole and the geographic pole, I should say, are not perfectly aligned. That means if you are navigating using a compass magnetically, there is an 11.5 degree offset. And this offset's actually getting worse. And it actually turns out that occasionally the magnetic field of the Earth actually completely flips upside down. This is something we've found from geological record, that periodically Earth's magnetic field flips, and it happens quite quickly. Every few hundreds of thousands of years, I should say, the magnetic field flips upside down, the South Pole becomes the North Pole, and the North Pole becomes the South Pole. No one's really sure why this actually occurs, but when it occurs very quickly over a period of 100 or so years. It might even mean that there's a period during this flip where we're without the magnetic field's protection. Now, why do we need the Earth's magnetic field's protection? Without the magnetic field of the Earth, the solar wind as it's referred to, charged particles coming off of the sun here, move across space and hit the planet. This is the kind of thing that a planet without a magnetic field, such as Mars, has serious problems with, as the magnetic field picks up these charged particles and actually buffs them out of the way, actually acts like a bumper and gets rid of them. They essentially get channeled away. A lot of the particles get picked up, however, and channeled onto the north and south poles of the Earth. And that's where they actually excite the upper atmosphere of the Earth, giving off light and resulting in a plasma. And that gives you pretty auroras to look at. This is a picture from Finland. So, the Earth, very much like a bar magnet. Take a north pole and point it and take a compass, and take it outside. It'll point towards the North Pole. What we call the North Pole, the geographic North Pole. But stop and think about this for a second. If the compass is pointing to a North Pole, that must mean that it's actually a South Pole. So the magnetic field at our North Pole is actually the south end of a magnet. Think about that one. I won't put it on an exam. It's okay. So how can we use this? Well, we can take something like this. Take this situation. If we have a wire and we run electrons through it in a current, so we're causing electrons to flow down through this wire. that will cause a magnetic field to be set up by those moving currents. And this is what Einstein's general relativity was really talking about, the magnetic field and the effects of a magnetic field from a moving charge. So the charge is moving this way, that will result in a magnetic field that spirals this way. If we put our compass in the field, the compass will point in the direction of the magnetic field. Take a whole load of compasses and put them around your wire and turn the wire off so there's no current in this wire currently. All of these compasses will point towards Earth's North Pole. Turn it on, the current runs through this wire and you can see the direction of the magnetic field as a result of these moving charges. Now note the direction of the magnetic field in this diagram versus the previous diagram. It is opposite, and the direction of the magnetic field does depend on the direction of the current you apply. And in this way, we're going to see this when we talk about solenoids, we can actually twist up our magnetic field and we can produce what's referred to as a solenoid, an electromagnet essentially. So our current will go through this wire, generate a nice magnetic field that curls around, but as the line is twisted up, as the wire is twisted up, the magnetic field inside will become straight inside here. So this is essentially a bar magnet that you can put things inside of. So here is an electromagnet. Now, if we were to take a particle and put it into a magnetic field, and this has to be a charged particle, so it either has to have a positive or a negative charge. If it's a neutral particle, a magnetic field will have no effect on it. But take a charged particle with some charge Q and introduce it to a magnetic field. If that particle is stationary, the particle will feel no force. If the particle is moving, has some velocity v, then the force that that particle will feel will be q times v cross b. And remember, this is a cross product. So this could be qv b sine theta in a lot of cases. And we've seen this kind of thing before when we've dealt with torque in a mechanic sense. So the magnitude of the force here, we can ignore the cross there, the magnitude will be QVB for the force. Now, there is a very specific case when the force is the maximum. V here is 90 degrees to B. B is the symbol for the magnetic field. We used E for electricity already. M is already gone in terms of mass. So B is your magnetic field. So here's your B field pointing this way. And at this point, I usually like to show a nice little model that I have of this. But here is B. If our particle is moving at a velocity 90 degrees to B, the resulting force will be 90 degrees to both V and B. And this is extremely important for some of the questions you're going to be asked in the coming assignment for this particular module. Our velocity is this way. Our magnetic field is 90 degrees to the velocity. This will cause a force 90 degrees to both V and B, hence this cross product. Because it's a cross product, the force really becomes QVB sine theta, where the maximum is when they are at 90 degrees to one another. Remember, this is a force, so it's going to come out in newtons. Here is a charge 90 degrees to the magnetic field, moving with a velocity 90 degrees, should say. This will experience a maximum force 90 degrees to both B and V. If your particle, because of this formula QVB sine theta, is moving in the same direction as the field. So here's the field going this way, here's the velocity going this way. You'll end up with zero force acting on this particle. So maximum force is moving 90 degrees, cutting through the field lines. You'll have zero force if you're not cutting any field lines and are just moving with it. And anything in between, you would have to know the angle and have to find QVB sine theta. So bear that in mind when you're looking at these problems. Does a problem say the velocity is perpendicular to B? Does it say B is perpendicular to the velocity, or where is B in relation to the force if you're asked to find V? Now, I've said this, but now I want to add one little caveat, that we're looking here at positively charged particles. And the way you should always calculate this, the way I always calculate this, is I calculate everything and figure out the direction as if my particle is positively charged. Then I say to myself, I have a negative particle, and I do the opposite. Now, doing the thing with your fingers and pointing in the directions and saying this is force is 90 degrees to velocity, which is 90 degrees to magnetic field, is great. Do everything like that as if it's positive. Don't try to dislocate your wrist trying to simulate a negative particle. Do everything like it's positive, and then if it says your particle is an electron instead of a proton, or just negatively charged instead of positively, then reverse your answer. If we're looking at this situation, you have symbols, one of which is a circle with a cross, another that you'll see is a circle with a dot in the very center. Take a look at the diagrams in the book and make sure you can actually interpret these diagrams correctly. We'll see more as these lectures progress. But a circle with a cross is a magnetic field going into this page or into your monitor currently. If it was a circle with a dot in the center, it would be coming out of your monitor. So now we have to start visualizing things in 3 dimensions on a 2-dimensional screen. So in this case, this is B, and it's going into the screen. The velocity of this positively charged particle is this way, 90 degrees to B. That will result in a force upwards on this particle. So do the hand motion there. You've got B going in, you've got V going forwards, and that will result in F, 90 degrees to both, going upwards. Now, if this was a negatively charged particle, it would react in exactly the same way. It would just wind up going down instead of up. So let's take a look at a problem. We've got an electron. It's moving at 2 times 10 to the 6 meters per second, and it's perpendicular to a magnetic field, so a B field, having a flux density of 2 Tesla. The units of magnetic field are always given in Tesla. Now, in terms of magnetic field, 2 Tesla is a very intense field. Even if you go for an MRI or something like that, you're much more likely to have about a 1.5 Tesla field or 1 point something Tesla field inflicted on you. It's very rare to inflict a 2 Tesla field on something. So Tesla's one of those units where it's very, very big, and in your everyday life or any equipment you're using, you'll probably be in the milli-Tesla range for a fairly powerful magnet. But anyway, back to where we were. An electron moves at 2 times 10 to the 6 meters per second. It's perpendicular to a magnetic field with a flux of 2 Tesla. What's the magnitude of the magnetic force on the electron? So by magnetic force, all it's saying is what's the force due to the magnetic field, which is F, or we're going to use the little subscript here, FB. We are going to move to problems where we have electric and magnetic forces interacting. FB is magnetic, FE would be electric. So FB is going to be QVB sine theta. I realize the sine theta might be a little redundant here since it's perpendicular and 90 degrees, but I want to be extra careful here and show all of my calculation. So let's substitute in. F is qvb sine theta. That's going to give us, it's an electron, remember? So negative 1.6 times 10 to the negative 19 coulombs at 2 times 10 to the 6th at 2 million meters a second. Remember, nothing faster than 3 times 10 to the 8. 2 Tesla sine 90. That'll give us 6.4 times 10 to the minus 13 newtons. This is a tiny force for a large magnetic field, but it's a tiny little charge. Take a look at another one. Let's take a particle with a charge of 6.4 times 10 to the negative 19 coulombs now, and it has a force acting on it of 2 times 10 to the minus 12 newtons. It's traveling now through a 3 Tesla magnetic field, so get into crazy Teslas here, at an angle of 30 degrees to the field. What's the particle's velocity? So this is all a matter of question interpretation. Again, F is going to be qvb sine theta. Our velocity will be a rearrangement of that. We have the force, we have q, b, and we have the angle. 30 degrees again. Plug them all in. This will give you about 2 times 10 to the 6 meters per second. Always make sure you're not exceeding the speed of light. So the magnetic force on a moving charge can be calculated by F equals qvb sine theta. You could also, of course, calculate B. So again, you could rearrange this, determine B, essentially exactly the same methodology. Here you've got a proton moving 90 degrees to a uniform field at 1 times 10 to the 7 meters per second, and this time has an acceleration of 2 times 10 to the 13 meters per second per second. I apologize for the units flub there. In the x direction with its velocity in the z direction. So 90 degrees to one another. Find the magnitude and direction of the B field. You've got an acceleration here as opposed to a force. But F equals qvb sine theta. Sine theta, of course, here is going to be 1 because it's 90 degrees. Giving you B is F over qv. The reason I'm showing this and repeating the same equation for the third time is that if you are given an acceleration, don't forget to go back to mechanics and invoke the fact that F is equal to ma. We can now substitute in and say B is going to be ma over qv. And you can kind of see what this is going to do to the units with a here and v here. Essentially, we're looking at ratios of m to q. So mass is the mass of the proton. Charge is the charge on the electron, essentially, but positive. So B is ma over qv. Substitute in, here's our 1.6 times 10 to the minus 27, 1.6 times 10 to the 19, 2 times to the 30. This will give you 0.021 Tesla. Like I said about the Tesla, you do have to be somewhat careful. Tesla is the SI unit of the magnetic field, and the charge on 1 coulomb moving with 1 meter per second at 90 degrees to the magnetic field will end up with a 1 Newton force due to the 1 Tesla field. So 1 Tesla is 1 Newton per coulomb over meters per second, or 1 newtons over amp meters. Bit of a mouthful. Or the Tesla. That is the definition of the magnetic field. And like I said, it's a big unit. B for the Earth is 10 to the minus 4 Tesla. That is the Earth's magnetic field at 10 to the negative 4. Have an MRI, you'll have a 1 to 1.5 Tesla field. Magnetic fields over about 10 Tesla tend to completely destroy whatever machine you're using to create that magnetic field. It kind of collapses it and destroys it. So we don't really see any fields over 10 Tesla that are created artificially. There are such things as neutron stars or the magnetic field of black holes, which are immensely powerful, which we won't necessarily get into here. Here is Tesla, though. I don't want to talk about Musk and his irritating antics. Here is Tesla himself, and here's his pigeon. Tesla had something of a tragic life. There are a lot of Tesla fanboys who like to talk about this guy, often elevate him to superstardom. Very smart man. He did a lot of good work and was very ahead of his time in a lot of his ideas, such as charging without wires and things like that, transmitting electricity through the air. Unfortunately, he was also very difficult to work with and had a few problems. And at the end of his life, moved to New York and, I am not joking, fell in love with a pigeon. I don't know if that's the actual pigeon. So, Tesla, nice guy, very hard worker, a lot of great ideas, but had his issues. Finally, I just want to mention this. As I said, the Tesla is a huge unit, and a small and very common replacement for the Tesla is the Gauss as a unit. And 1 Gauss is 10 to the negative 4 Tesla. Now, I always encourage the use of SI units to make sure that your numbers come out well. But I should say that even textbooks like to use the Gauss, and the Gauss pops up a lot. It is not an SI unit. If you are given a problem even out of your textbook that is in Gauss, please make sure you correct it to Tesla before you proceed. I will never give you an assignment or an exam using Gauss. I will always use Tesla, but be careful with other sources.